T&D explains, and this is applied physics 1034. In this video, I'm going to introduce one of the most important foundations in physics, which are vectors. You learn how to represent them, break down into components, and how they are used to describe real-world quantities like displacement, velocity, and force. I'm going to keep it clear, simple, and visual. By the end, you'll know exactly how to work with vectors. So let's begin. What is a vector? A vector, as we might know it, is a quantity that has both magnitude and direction. Vectors are used in physics and engineering to represent things like forces, velocity, acceleration, displacement, etc. Imagine that we have a force of 5 Newton acting northeast, and the direction is northeast. It has both housed around the force is and which way it's going. Alright. And yeah, the next important thing is called vector components. And usually a vector has 3 components, namely the x and the y and the z component. Okay. So in 2D or 3D space, okay, a vector is split into parts called components along the coordinate axis. So in 2D, it's going to be A being written as AX I plus AY J. Okay, let's say this vector is something that looks like this. That means we move a certain direction in the x direction and the certain distance in the y direction. Okay, not distance per se, but it could be a velocity vector which first move in the x direction, the y direction, given this resultant. So if I have represented a certain vector A, it means that A is here and AX and this is AY. Okay. And yeah, we do have these things called unit vectors, which are written with heads. I'm going to explain what is a unit vector in a second. Okay, and then in 3D, the same as another similar vector can be written as A is equals to AX I plus AY J plus AZ K. Okay, the third component is the component that is coming out of page. So if we have AX going this direction and AY maybe this direction again, the third component is the one that comes out of page. Okay, so how do you get magnitude in 3D and in 2D? I'm starting with 2D. So the magnitude of this vector A, please note that A can be written with a line at the bottom, and it can also be represented by an arrow at the top or whatever. There are different ways to represent vectors. I usually prefer putting a line underneath. So A, the magnitude of this vector A, because each and every vector has a magnitude and it also has a direction. The magnitude is given by square root, and you square all the components. So it's going to be AX squared plus AY squared. Okay, similarly in 3D, we're going to use the same formula. However, we also add another component, which is AZ. So it's going to be az squared. Okay, and another way to represent this vector a, it can be in terms of ax comma ay. Similarly, for in 3D, it's going to be ax comma ay comma az. Okay, and what's next? It's me explaining to you what are unit vectors, right? A unit vector is a vector that has a magnitude of 1 used to indicate direction. Okay, any vector that has magnitude 1 and can be used to show direction is called a unit vector. And a unit vector can point in any direction in 2D or 3D space. It's not just limited to x, y, z. So if you are given any vector, let's call it a again, and it has the components ax comma ay comma az. It can be turned into a unit vector. We can make a unit vector out of any vector. The formula that we use is that unit vector n is going to be equals to the components ax comma ay comma az, and then you are going to divide it by its magnitude, which is going to be a. Alright, then you've got yourself a unit vector. I gave you the formula for the magnitude of a, which is where you square all the components and put everything under the square root. Okay, so let me make an example. Given the vector a being equals to 6 comma negative 3 comma 2, the magnitude of a is going to be equals to 6 squared plus negative 3 squared plus 2 squared. This equals to square root of 49. We do know that the square root of 49 is going to be equals to 7. Okay, so the unit vector n, or sometimes other people call it u. I think it's better to call it u and put a head just to show that it's a unit vector. Okay, now it's going to be 6 comma negative 3 comma 2 divided by what? By 7. So your final answer is going to be equals to 6 over 7 comma negative 3 over 7 comma 2 over 7. Ultimately, you can say that it's going to be 6 over 7. I had recall that I represents a unit vector in the x direction, plus or minus negative 3 over 7 j comma plus 2 over 7 k. Now you have your unit vector, right? And we can also perform a check, because we said that a unit vector has magnitude of 1. So I'm going to check the magnitude of u. It should be giving me 1. U is going to be equals to the magnitude of u, which is going to be the square root of what? 6 over 7 squared plus negative 3 over 7 squared plus 2 over 7 squared. Now, what is 6 squared? 6 squared is going to be 36 over 49 plus 9 over 49 plus 4 over 49. 9 plus 4 is 13. So 36. Okay, because we have the same denominator, is going to be 49. So I'm gonna add everything. 9 plus 4 is 13, like I said, plus 36 gives me 49. I put everything under a square root. I get my answer as square root of 1, which is ultimately 1. So yes, it's a unit vector. A unit vector has magnitude of 1. This is to show you that any vector can be a unit vector. Any vector can be turned into a unit vector, because if we have, okay, let me show you something very quick. Do you see this vector that we were given at first? We were given the vector 6, -3, and 2, this one. Okay, so what does u represent? If we have a vector 6, -3, 2, it means we are moving in the x direction 6 units first, then we move -3 in the y direction. Is going to be like this, and then we move 2 out of page. So there is no way I can represent out of page, but just know that it's somewhere here. And then where we started, let's just say this is going to be something like this. And yeah, it moves upward, like it's, this whole arrow is coming towards you, and it moves to the right 6 units and 3 units down. So a unit vector is just a vector in that same direction, which has a magnitude of 1. So it comes out like this. It only has a magnitude of 1, and we saw this vector has a magnitude of 7 here. Okay, but the unit vector on its own has a magnitude of 7. It's me finding a vector in the direction of a certain vector which has magnitude 1 and is also dimensionless. It's not just all about I, j, k, because I told you that I and comma j and k are all unit vectors, where I is a vector with magnitude 1 in the x-axis direction. So I is going to be equals to 1, 0, 0, and j is going to be what? 0, 1, 0. And what is k? K is going to be equals to 0, 0, 1. And to confirm that they are unit vectors, we can use that formula for the square root, and you will see that you always get a magnitude of 1 for each and every unit vector. Okay, and yeah. And so if we have like a 3D coordinate system, let's say this is the z direction, and then this is a y direction. Let's call this x direction. This is the y direction, and let's say, actually let this be the z direction and let this be the y direction. The unit vector is going to be something like this. And this is going to be what? J, the vector j, which has magnitude of 1, 0, 0. Okay, and this one is going to be I, which has the magnitude of, actually this is going to be 1, 0, 0, and this one is going to be 0, 1. Okay, for the z, this z is what? This one is going to be k, unit vector k is going to be 0, 0, and 1. Okay, another important concept is the principle of transmissibility. Okay, so what does the principle of transmissibility say? It says that any force can be moved along its line of action without changing its external effect on a rigid body. Rigid body being a body that cannot be destroyed. Recall that. What does it say? You can move a force along its line of action without changing its external effect on a rigid body. A rigid body, like I said, it's a non-deformable body. And what is meant by a line of action? Suppose that we have a force which points in a certain direction, and the line of action basically is this line that continues to follow the direction of the vector, actually, not a force. Okay, so yeah. And yeah, in this case, we're applying this principle in terms of forces. It says that you can move a force along its line of action without changing its effect on a rigid body. Let's say we have a rigid body. That means this body it's non-deformable. It means that if I apply that force here, it's going to move in a certain direction, and we do know that this direction is this one, right? What the principle of transmissibility is trying to say is that if I can take this force, copy it and paste it, put it in the same line of action, all right, the effect is the same, so it's going to move in that same direction. Another example is, let's say you push a table with a force of 10 newtons to the right. It doesn't matter where on the side you push, as long as the direction and line of the push stay the same. The table is going to move the same way. And yeah, one thing to note is that the principle of transmissibility only applies to rigid bodies. Okay? And we do know that it also does not change the force effect on the motion of the object, like translation or rotation. Yeah. And yeah, this thing is useful in free body diagrams and in applying equilibrium equations. The principle of transmissibility is also related to sliding vectors. Okay, a sliding vector is a vector like a force that can be moved anywhere along its line of action without changing its physical effect on a rigid body. So yeah, it's just another way of saying what transmissibility allows. You can simply say that a sliding vector is a vector, a type of force vector, okay, that uses the principle of transmissibility. Okay, and yes, that's the end of our introduction. On the next video, I'll be focusing on examples and past spot tests.